Hi, I'm here to talk to you about discrete probability distributions. And what I'm going to do is I'm going to build from the PowerPoint that I had previously. Come on. And basically talk through this. A lot of what you're going to hear is what I would have said, or I did say in the uh, PowerPoint with audios, but since I couldn't figure out how to transfer that into Zoom, we're going to go on with this, do it this way. Anyway, I want to talk about discrete probability distributions. And this chapter, the last chapter was on classical probability and some basic concepts about probability. This is about discrete probability distributions. The next chapter will be about continuous probability distributions. I want to mention that this builds on previous concepts. Before, what you've heard me talk about concepts of, with the second chapter, I think it was, we talked about a frequency distribution, a relative frequency distribution, and a cumulative relative frequency distribution. We're going to have the same things here, except that this time, instead of talking about numbers, we're talking about probabilities and trying just to expand those concepts for them. We're working again with, said that. Let me start with an example here. Suppose I have a school, and in my school, students can enroll in January, April, June, or September. And I have data about how many people have enrolled each of the last 5 years and each of those 4 time frames. The totals are down the center here, the 100, 150, 125, 225, the total is 600 here. And then the average per year is over here in this column here. If you take 120 and take 20 and divide by 120, it gives you this proportion, this decimal, which is the proportion of 120 that 20 is. 30 is 25%, or 0.25 of 120. 25 is 20.8%, and 45 is 37.5%. That's beginning of a frequency distribution. If I want to have a frequency distribution, it would be something that looks like this. This is the probability based on historical data of when someone might have enrolled in the school. If you came to me and said, "Hey, I enrolled in your school this last year, but you don't know me, and can you guess when?" My best guess would be September, because that's the largest, that is most probable out of all the 4 times that are here. I would note, for instance, that again, the January, April, June, and September are discrete periods of it, as opposed to continuous enrollment, which you can enroll in any given day of the week, for instance. And this right here is, in fact, a probability distribution. One of the things about a probability distribution is it always ends up totaling to 1.0. If you take all your probabilities and you add them up and it comes out to 1.2, you've made a mistake. If it comes out to 0.85, you've made a mistake. That somehow, if the total number, the sum of all the probabilities in a probability distribution should be 1. That's what it is every time. Now, one of the values of something like this, getting a good frequency distribution, is it allows you to create a cumulative proportional frequency distribution. In this case, in the cumul prop frequency column, the cumulative proportion of people who enrolled in January is 0.167. Same number who actually do it. However, the cumulative proportional frequency in April is equal to 1.167 plus the 0.25, which is the numbers that fall in the April enrollment. The next one is 0.625 for June is equal to the proportional frequency, the cumulative proportional frequency for April plus the frequency for June. And the one, which is the total here, that means everybody, we got everybody now, is the 6.25 plus 0.375. If we have something like this, what happens is this year, I can look at my numbers, the number of students who enrolled, and say in January, I have 22 students enrolled. Off that, I can project what my total year enrollment would be. The way I do that is I divide 22. I divide 0.167 by 22, and it gives me, or maybe it's the other way. I divide 22 by 0.167, and it gives me 132. That's my projected for the year based off my January enrollment numbers. Well, I come to April, and now I've got a cumulative number of enrollments for the year of 42. If I divide 42 by 0.417, I come up with my projected is now down to 101. Now that may make some sense to you, because if I go over to the average per year, on average I have 20 students. Typically, my first quarter this year was a good quarter. I got a little bit better than that. My second quarter, I typically have 30. Well, what I have is I have another 20. So my enrollment's really down for the second quarter. It gives me a projected enrollment of 101. This is what a cumulative proportional frequency distribution gives you, because what you get here is you'd say, this is what I can expect in terms of the number of students enrolled. This percentage, this cumulative proportional frequency, is the percentage that I expect to have enrolled by any given point. I can take what I actually start getting in the cumulative, so what I actually got this year, and gives me a way of projecting what I've got out here. The value of this for you in a managerial or managerial positions generally is, if at the end of two enrollment periods, I have 101 students, I have 42 students enrolled, I'm projected 101. That means I'm going to fall, if things keep going the way they are, I'm going to fall short for the year. And what that means is I'm probably going to be spending more money than the number of students that I have. Most budgets are based on a specific number of students. If my student enrollment's down and my budget stays the same, I'm in trouble. Now, somebody might look at that and say, well, gee, Steve, but the fourth quarter is that September one. That's the one where the really big numbers come. It's like, well, given where I'm at right now with 101 students projected, fourth quarter's got to be good. It's got to be better than usual, quite frankly. It gives you a way to start projecting ahead what's going on, helping you think about, are we going the way I expect we should be going, based on our historical numbers? Now, here's a piece of it that if I were doing this year and coming up with these sorts of things, I'd say, we're in some trouble. I'm not sure how we're going to do. If this were 2020, in the middle of the COVID crisis, I would say, I don't think these numbers are going to predict anything because we got special things going on in the world around us. So it would not be useful in a setting where special things are happening, and like COVID was for us at that point. In a typical year, these numbers might be useful. But this is a way of starting projecting out into the future and using probability as a way of projecting, because we know what the proportion of people, the cumulative proportion of people of our enrollment we've got at the end of 2 quarters. We know what we actually have at the end of 2 quarters, then help us get the projected numbers. Very helpful information if you're managing a program. Let me give you different kinds of scenario here. Suppose I have a generic oil company and we dig wells, oil wells. And over the past 5 years, say, we have dug 500 wells. And based off of that, half of them, 0.5%, 250 out of that 500 have come up dry. They didn't give you anything. And in each case, I lose $80,000. That's what it cost me to dig a dry well. So I dig a well, I got nothing. I've lost $80,000. And that happens 50%. That's happened over the past 5 years, the last 500 wells. That has happened 50% of the time. 250 out of 500 wells came up dry. Going down a step further, an okay well, 30% of the time, we've got dug a well and it's done okay. It's generated about $100,000 for us. Now, that's not bad. And 20% of it, 0.2, have generated $500,000 each. This is pretty good news. Now, I'm going to assume here this 100,000 and 500,000 is actually, it actually generates 180,000 and 580,000 to take care of the $80,000 cost of this thing. So these are net numbers in the far right-hand side. Well, one of the things you think about that is, well, should I keep going? Because half the time I'm losing money here. Well, you can use the same process, which is a thing called expected value, to get at this. The way you figure out an expected value is you multiply the frequency by the net amount in this process. In this case, for a dry well, half the time, 0.5 times that, times $80,000, negative $80,000, gives me a negative $40,000. 0.3, 30% of the time, we gain $100,000. So 0.3 times 100,000 gives me plus $30,000. And 20%, we get $500,000 of that for each one of those. So 20% times 500,000 gives me $100,000 as the outcome. Then you add up those numbers in the far right-hand side, the expected values, negative 40 plus 30 plus 100, and you get $90,000. That's the expected value for digging a well, is $90,000. Now, that doesn't mean that I go out and dig a new well tomorrow and I'm going to make $90,000 off it. Chances are I'm going to go out tomorrow and I'm 50% chance I'm going to come up with a dry well. But if I do 10 of them, I think, well, again, 5 of the 10 should probably come up dry. But 2 out of those 10 are going to give me $100,000 each. So on average, the expected value is $90,000. Now, you think of that and say, well, that's not a lot of money to make off, this sort of process, Steve. And I'd say, yeah, except that if I drill 100 wells and these proportions hold true, that would generate $9 million. And then we start talking about money that's worth paying attention to. Now, truthfully, oil would be willing to probably add $1,000 on it, or at least another zero on every one of these things. But I'm trying to keep this simple. And let me say, if I were doing a drilling an oil well, there'd probably be at least 5 or 6 different categories off here to the right, because there's got to be something between a dry well and an okay well, and something between an okay well and a gut. But I'm trying to keep this simple. That's the point here in this process. Expected value is the sum of x's times the probability of x. In this case, it's put out in my chart here. It should probably be probability of x times x. I've reversed them on here, but that's the formula, baby. The sum of the probability of something times the value of it. And then you sum those things up. In this case, it comes up $90,000. You may also hear someone talk about the mean of a probability distribution. That's the same thing as the expected value. is the number that's supposed to come up, will come up most commonly in the process. Let me give you a different kind of setting. That's one that, and I'm going to talk about the difference between these two in a minute here. Suppose your great uncle Harry dies and he leaves you $10,000, which for you is like found money. It's like you don't expect that. And you think, I'm getting by, but I should probably invest this $10,000. And you go to your friend Bill, who's an investment guru, and Bill says, I got two options for you, option A and option B here. Let me tell you about them. In option A, there's three possibilities in it. Either way, I mean, you put your $10,000 in, regardless one or the other. Your money's gone. It's what's called, accounting is called a sunk cost at that point. You've turned the money over, it's lost. The question is, what's the likely financial gain in three different settings here? And in one case, outcome A for option A is zero. In other words, you get nothing back. Not a good thing. Outcome B is you might get $20,000 back, and there's a 0.5 probability of that. In outcome C, you get $100,000 back, and there's a 0.2 or 20% chance of that. Now, again, I note for the probabilities on the right add up to 1.0. They always have to. Option B, very similar thing. You put your $10,000 down, and outcome A again is you get nothing. You lose everything. Now, unfortunately, with option B, there's a 40% chance you're going to lose everything in that one. Outcome B in it is you make less money. If you only make 15,000, this option A is where it's 20,000, but the probability that's only 0.3. And outcome C is you get $100,000 back, and there's about a 30% chance of that. So there's a better chance of making it big on this one. How would you decide which one of these things? You trust Bill, that Bill would send you, he's given a fair presentation of what's out there, and you're going to go, how would you decide between these two? Well, let me show you. It's an expected value problem. In each case, you go back to that formula, the sum of the probabilities times the value. In option A, outcome A, opportunity A, you lose $10,000. So you have a 30% chance of losing $10,000. That gives you a -3. Option B, you gain $10,000. I mean, you gain 20, but you put $10,000 down, so you only get 10,000 additional dollars back, and there's a 50% chance of that happening. And outcome C, you get $100,000 now again, but that's only the net part of that is only 90,000. There's a 20% chance of that, and you add those up, -3 plus 5 plus 18,000. And you get $20,000. That's the expected value for opportunity A. You do the same look at opportunity B, and you can go through the numbers here yourself and sort of take some time to think about that. There, the expected value comes out 24,500. So strictly from a financial perspective, you look at these things and say, well, opportunity B has a better expected value than opportunity A. The value of this sort of approach is you're using a consistent way to evaluate two complex alternatives. And it can give you a sense of which one's mathematically, which one's the better one you want to work with. Now, however, two things about this. Putting your $10,000 down is not just a mathematical decision. It's also an emotional and intuitive decision. There are other things going on in the world, and you listen to those things and say, Each of us has a thing about what we call a risk aversion, our level of risk acceptance. I look at a 40% opportunity B, a 40% chance of losing my $10,000 and going, Boy, that gets me really. I don't like that very well at all. Um, so even though opportunity A doesn't pay off as well, I have a smaller chance of losing everything to opportunity A, and I might end going that way. This differs person by person, and the point I want to make about this is complex decisions like this are often made on the basis of intuition, or I like the name of the company of company A better than company B, or all sorts of. My wife talks about times she buys wine based on how well she likes the label on the wine. It has nothing to do with what's inside; it's how cute's the label. That those are intuitive, or those decisions are based on a variety of things. The mathematics of it can tell you which is the better likely outcome here. But the decision is not just a mathematical decision. The mathematics can help inform your decision making, but it should not be the basis for all of your decision making. Now, let me make another point here, which is really crucial about this one. The difference about expected value here from this case versus the oil case I was just showing you a few minutes ago is, in the oil case, it's my company. I'm probably gonna dig 100 wells this next year. I'm gonna repeat that process 100 times. Given the expected value is positive, I'm gonna make money probably. Unless something else has changed in the world, almost guaranteed I'll make money in that kind of process. With this situation here, you're choosing between two things and you're only gonna do them once. So the expected value gives you some information about it, but it's not the same sort of situation as when you're going to do something over 100 times. You are not going to go invest $10,000 100 times here. You got $10,000, you're going to do something with it. Your intuition has to guide part of it. Expected value can add some information to inform your intuition. And that's something I value a lot, basically, because I tend to see myself as a very intuitive person in a lot of ways. But what I'm doing here is I'm trying to say, how do I give myself the best information for making an intuitive decision, making a leap of faith, if you will, in the process. That's the difference between these two scenarios we have to work with. And I may try to throw something out this week about how, if one were going to do a lottery. I recently bought a lottery ticket for $100. Now, one of the things about lotteries is expected values of lotteries are always negative. If you buy a lottery ticket, you have to expect to lose. Now, I bought a lottery ticket for $100 because, one, it supported a nonprofit organization that I support and I feel pretty good about. That's one thing. That's not good enough for me typically. The second thing is these people say they're only going to sell 150 tickets. So I've got one chance at 150 of winning this lottery. It might be interesting if you go buy a lottery ticket for something like Megabucks or the other big lotteries. Stop and see what your odds are of winning. And the odds in those things come out to often like 1 in 363,275,481. You're going to go in, so that's a real long shot. I'll risk $1 on that. I might even risk $2 on that if the prize is big. But the truth is, if I buy a lottery ticket, I expect to lose. And if a lottery expected value comes up positive, what that means is the people running the lottery are going to go broke. Because if I can expect, if I buy 100 tickets, on average, I'm going to make money. That means the people who are running the lottery, on average, are going to lose money. And they do that in any kind of consistency, and they're going to be out of business. It's got a lottery thing from somebody calling to say, "Oh, you won a brand new car," and this for. I'm going, wonder who pays for that. because you don't just give things away without some sort of income to buy the things you're giving away. Uh, but lotteries are one of those places where my expected value is negative, but I may go ahead and do it because I spend $2 on a one of the big lottery things. And what it buys me is I can spend the evening thinking about, well, if I win $73 million or $2.1 billion, what I would do with it. And I can indulge myself in the fantasy overnight that I could win this. Now the odds of me winning are really bad, but they're not zero. So that's what I'm purchasing. I'm purchasing the fantasy for a day, and for $2 I'll do it. Expected value is a way to put some numbers to inform your decision making. And that's an important piece. Change in subject here. Binomial distribution. This is a very useful, specific kind of discrete distribution. And actually, more accurately, it's a set of distributions. I wonder what I mean by that. Let me just give you an example here. Suppose I flip a coin, heads or tails. The probability, assuming it's an honest coin, is 0.5. And you can do this an infinite number of times. You can sit as long as you maintain enough interest to do it, stay awake, you can keep flipping coins and just keep adding two things here in this process. It's a binomial problem, if you will. With one flip of the coin, you get a 50% chance of heads and a 50% chance of tails. That makes sense. You can go either way, assuming it's an honest coin. With two flips of the coins, you can get four different kind of possibilities here. You get two heads, tails, heads, or two tails. Now I put the middle piece here I call HT. This is one of those places where I'm talking about a combination as opposed to a permutation. On the left-hand place, where I got HT/TH, then I'm talking about the permutations. What I'm doing is saying, I don't care which one I get, heads, tails, or tails, heads. What I care about is I got one of each. That's the combination that I'm looking at here. And what's the probability? What I've done on the left-hand side is I've sort of laid out the possibilities of what could happen with two flips. What I've done on the right, if you ignore the comma before the first 2-5, which should have been a period, I'll give you the probability distribution for a binomial probability distribution with count of 2. With count of 3, it's different. With count of 4, it's different. However many attempts you make overall, that becomes a really important piece in determining which binomial distribution you're working with. And because each of them has slightly different numbers. And I'll show you how we get to that one a bit here. With 3 flips of the coins, I can have 3 heads or 3 tails. And then I've got 2 heads and a tail, 2 tails and a head as middle possibilities here, combinations of things. And to the right here, I've got the probabilities of each of those. The way I get those probabilities, I can kind of go on, well, 3 flips of a coin, there are 8 possibilities. 3 heads is one of those 8s. 1 divided by 8, it gives me a 0.125. That's for the 3H and also the 3T. 3 flips, the HHT, HTH, and THH permutations go into a combination category, which is 2 heads and 1 tail. And those 3 divided by 8 gives you a 0.375. That's the probability there. That's how I'm getting the probability numbers for a binomial distribution with 3 cases, with 3 attempts, which gives 8 outcomes. Now, I've done 4 flips down here to give you that one. Now there are 5 different kinds of possibilities with 4 flips. You can get 4 heads, 4 tails, 3 heads and 1 tail, 1 head and 3 tails, or 2 heads and 2 tails. Those are different possibilities, and you can count the things out there and say, well, those are the probabilities of each one of those things. Now, you might notice 1 flip, there are 2 possibilities. 2 flips, there are 4 possibilities. 3 flips, there are 8 possibilities. 4 flips, there are 16 possibilities. 5 slips, there would be, and this is where the fundamental counter rules. How many possibilities are there? Well, there are 5 things, and each one is, there are 2 possibilities. So it's 2 times 2 times 2 times 2 times 2 comes out 32. That's the fundamental counter rule. You can figure out what the denominator is for doing the probabilities here. And like the probability for 4H is 1 divided by 16. If I had 5 things, I could go 1. The probability of getting 5 heads would be 1 divided by 32. You can start laying this out. You can start figuring this out yourself. You would sit down with pencil and paper and do the work like I've done this sheet. Now let me take you do a slight variation on this one. These are the probabilities of each discrete number, for each discrete category in this situation. What if I asked you, what's the probability of getting at least 2 heads? You go, well, which one of these kings down here would count on that? Well, the center one would be 2 heads and 2 tails. And the 3 heads and 1 tails gives me, I still would have at least 2, so that would count on it. And the one with 4 heads would count on that also. So the probability of getting at least 2 heads would be 0.375 plus 0.25 plus 0.06. Interesting. The probability of getting at least 2 heads would be the same as what's the probability of getting up to 2 heads? Again, you could end up adding up the 4 tails and the 1 head and 3 tails and the 2 heads, 2 tails, and come up the same number as in this case. In those cases, we're talking about cumulative probabilities, as opposed to what I think of I will call it in the course here, a point probability. What's the probability of getting exactly one head with 4 flips of the coin? Well, that's the category is 1H3T. And the probability of that is 0.25. That's the point, the probability of getting that specific point. A cumulative probability of getting up to and including 2 heads would be the, let me go back. Sorry, I'm got ahead of me here. Probably getting this one plus this one plus this one and adding up these probabilities. That gives you a cumulative probability. Well, the good news is you don't have to do the mathematics of this much because in Excel, there is a formula, binom dist. And for instance, what I'm doing here is saying, what's the probability of getting 2 heads, tails, whatever you want here. And that means up to that number. On 4 trials, the probability of each outcome is 0.5. And then there's a thing down here that says cum. Excel does a funny thing here. They ask you to put in either true or false. And a true gives you the cumulative probability, a false gives you a point probability. And you put those things in, and it'll actually tell you right there on the screen what the answer is to that. Easy formula to use. Figuring out what those numbers are is important, however, and can be a little challenging. I can go back here, for instance, this is the case we're just talking about, and sort of walk through with these numbers and show it. I'll leave that to you. The key points I want to make about binomial distributions are, 1, the probability distribution always adds up to 1. When you're doing this, you want to think about how many trials do you have and how many successes. If you have 4 flips of the coins, you have 4 trials. A success, you count heads or tails, wherever you want to. The successes is how many of one of those things comes up. The probability of success, the coin flip, an honest coin, is 0.5. In other situations, it is not that. It could be a different number. So you got to pay attention to what's the probability of it. And the fourth piece is, am I looking for a cumulative frequency or a point frequency? Now I tell you, when you get a word problem from me working on this stuff, what you want to do is stop and look at read my language carefully. If the problem says, what's the probability of getting exactly da 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 da, we're talking point probability. Exactly means one specific point. If the language says, what's the probability of getting at least da 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 da, or as many as da 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 da, or what's the other possible I'm going to do with that one? Up to at least as many as, those sorts of things tell you I'm looking for cumulative probability frequency distribution. Important to keep those things in mind. The binomial distribution is the key one here. It's the one you really want to pay attention to. I mentioned a couple others, and I want to go back and talk about these briefly. One I mentioned, I'm not really going to give you the formula or ask you to do anything about this, is a hypergeometric distribution. The binomial distribution assumes independent trials. The hypergeometric says, nah, they don't have to be, they're not independent trials. And let me just mention here, for instance, let me just double check something for a second. Back someplace in this week's stuff, I give a short little thing that's a little TED Talk thing on how airlines sell tickets. And the way airlines sell tickets, if they have an airplane that has 100 seats in it, they sell 100, they try and sell all 100 seats. And you say, but because one of the other things airlines do is they look at that thing and say, historically, we know some people who buy seats are not going to show up. They're going to be no-shows for whatever reason. They got hit by a car, they had a late minute change of plans, they're decide to stay and visit their girlfriend for another day. Who knows why? Doesn't matter why. What you know is some proportion of people who buy tickets will not show up. So what airlines do on a regular basis for its plane that has 100 seats is they sell maybe 105 seats because they're counting on a certain percentage of people not showing up. And those, generally what we think of as those, what you have there, something we deal with in binomial distributions, is a dichotomous situation. They show or they don't show. Now you could say, well, but it's more complex than, it's like ultimately from the airline's perspective, that's really the only thing that counts. Do you show up on time or do you not show up on time? And if the answer is no, you don't, then you're a no-show. And what they do is they have information about the no-show rates on every flight, on every day, on every route. And you may take a flight from Pittsburgh to Orlando in the afternoon, and they could say, okay, the average no-show for that is da 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 da. And they say, well, how about from Buffalo to LaGuardia on Tuesday night? And they come back and say the average no-show for that is da da da, and they'll have all that information. Having that information, they use something like a binomial distribution to say, so if we have perhaps a 95% show rate or a 5% no-show rate, we can afford to sell 105 tickets and probably be fine without having to refund anybody any money. Because some of those folks, we don't make any guarantee that you can transfer that. You can transfer someplace later, but maybe for a fee, we'll add some money onto it. But it's like you basically, we can sell more tickets than we have seats because we know some percent of you are just not going to show for your flight. And we treat those that in that thinking, what we do is we treat show, no show as independent events. The mathematics of that is interesting. But as I was thinking about this one recently, I was saying, except that if person A shows or no shows, that's not always independent from other people, other no shows or no shows. If I buy tickets for me and my wife and my two kids, and I no show, chances are my wife and two kids are not going to no show. It's in some cases these are not exactly independent events. I don't know what the airlines do about that, but what they might do is they might in some cases apply a hypergeometric distribution for that kind of setting, where there is not complete independence between the events. Flipping a coin, yeah, flip one, flip two, those are absolutely independent events. No or no show, when you've got a family or you're traveling in a group, that starts being a little more tricky. And that one, they may have a hypergeometric distribution as one possibility. I just would note that for you. That I'm not teaching that. I just want you to know there are other ones around here. The final distribution I want to mention here is the Poisson distribution. It's not Poisson, Poisson distribution. And this is a distribution for the probability of independent events within a space of time. Suppose you're getting married this fall. Or you want to get married, but you want to get married on the Outer Banks of North Carolina. And you'd like to be married in the second week of September. But there are hurricanes, and sometimes they hit it, and the second week in September is it's kind of in the middle of hurricane season, So there's a chance that the weekend you're going to have your wedding there, they could have a hurricane there. And you're going, so what are the chances of that? Well, the way you do it is there's a set of distributions for doing this, and they're based off data about how often hurricanes come, that use a Poisson distribution for saying, here's the probability of having a hurricane on that particular weekend. And they can go back, even go into take weather service data and find out that information. And this is the kind of distribution, as opposed to a binomial distribution, because it has to do with a period of time. The Poisson distribution is the one that's a case in point here. I want to go back and make one final point, and for closing this stuff up here. There is what the binomial distribution does is it works with dichotomous data. And sometimes you have data or you have measures of things, and it's like, oh, there's lots of possibilities here, and they may all be nominal case. The data may be nominal, but I got lots of cases. Marital status is a great one. You want to check people's marital status? So you want single, married, divorced, widowed. Does remarried count? Does civil unions count? Does living in a long-term committed relationship where you don't have a legal agreement account? I mean, it's like the categories can just spread out. I know this because I was working with a data group one time that was trying to figure this out for a data system for adult education. And we got crazy trying to figure out, so what do we know? And why do we want to know this? Finally what we did is kind of said, stop. What we're going to do is, what do the feds require from us in this thing? The feds who provide funding to us, what information do they require? And we went back and read the federal regulations over, and they said, we want to know, does the person who's enrolled in your program have kids or not? We went, that's dichotomous data. Do you have kids or do you not have kids? One or more or 17, it's like, it doesn't matter, or 0. Do you have kids? More than this. Do you have kids living at home? Yes or no? You can sometimes take complex data and drop it down into simple dichotomous data and be able to work with it in some very interesting ways. The airline's doing that around show or no show. If you try to get the list of all the reasons people don't show for airlines and try and say, well, if they do this, we'll do that. And it's like the airline's position is, it doesn't matter why. The question is, at boarding time, are you there with a pass or are you not? Yes or no? Simple dichotomous thing. In our heads, some of these things are much more complex. But at some points, you can say, let's get down to the core here. Are you there? Are you not there? Do you have kids? Do you not have kids? And that's dichotomous data. And we don't tend to think of dichotomous data as being really useful a lot of times, but sometimes it's really useful and very helpful. And that's what the binomial distribution works with, particularly. And it's one of those places where it's worthwhile thinking about. I may have much more complex stuff here, but could my data be focused down into simple yes or no? On time, present on time, not present on time. Yes or no? That's dichotomous data, and that's what binomial distribution works with. And those are the key points from the discrete probability distribution unit this week. Have a good week.